Let's now talk about stack as an abstract data type. Earlier, we gave you the definition of what an abstract data type is. We also show you how to have an abstract data type of a list. And now we're going to talk about a stack. So let's first define what a stack is. A stack of elements of type T is a finite sequence of elements of T together with the following operations. Very similar to the previous one as a list, you could also create a stack to make it empty. You could determine if the stack is empty or not. You could determine if the stack is full or not. You could also determine the number of entries in the stack. If the stack is not full, then you could also insert a new entry at one end of the stack. Let's call it the top. If the stack is not empty, then you also could retrieve the entry at its top. If the stack is not empty, then delete the entry at its top. And lastly, you could clear the stack to make it empty. Now, really, the stack, if you could imagine this is almost like, when you go to a cafeteria where a stack of plate can be seen. And this is what exactly is a stack. Stack is an ordered list which all insertion and deletion are made at one end, which we call it the top. So if you in the cafeteria you see this stack of plates in this cart, what you could do is you put the plates, new plates on top of that, and when you take it out, you take it also from the top. You don't take it from the bottom of the stack. Hence, the fundamental operation on the stack is really push, which is to insert an element, and pop, which is a delete of the most recently inserted element. So many people actually have used LIFO, or last in, first out, to describe what a stack is. Here we see that we could create a stack. We could add or push some item onto a stack. You could delete or in some way pop. You could look at the top of the stack and you could check whether the stack is empty. Now, how would you actually implement a stack? On the left-hand side of this diagram, you can see that a stack, you could push something and you could also pop something from the top of a stack called S. One way of doing this is we could use an array. So if you were to use an array, you can see that here the shoe boxes are arranged vertically. So instead of horizontal, we just have vertical shoe boxes. And the top is the top of that shoe box. So as you insert items, this top will continue to rise. And when you delete or pop items, this top will continue to decrease. So here what we can see is that the number 3, 6, 1, and 4, now 2 is being pushed onto the stack. The next element that we are going to actually insert into the stack will be put it on top of 2, because you cannot put it anywhere else inside the stack. That's the definition of what a stack is. Now, as we say, we could use an array to implement this, but we could also use a linked list implementation. When you push, you insert an element at the front of the list. When you pop, you delete the element at the front of the list as well. And when you do a top function, you actually look at the element at the front of the list. So what is the time complexity of these operations to do push and pop? As you can see, if you have a pointer that points to the top, push, pop really is very straightforward and simple. They all will take constant time or order of 1. As I shared with you before, you could also use an array. For array, however, you need to declare the size ahead of time. Then you could use the top of stack as a counter for the size and the pointer to the top of the stack. And then the error testing may degrade the efficiency of an array implementation, but it is still workable. Let's take a look at how stack, the data structure, is used or can be used. One of the applications is a balancing symbols. For example, in the program, when you compile your C program, you actually, the compiler checks for whether there are syntax errors. And one of the potential errors is to check whether everything is balanced. For example, a pair of brackets, a pair of parentheses, whether they are even number of this kind of beginning and end bracket or parentheses. Moreover, you could also see that the second case is legal because they all have its pair. But the order of left bracket, left parenthesis, right bracket, and right parenthesis is not legal, functionally speaking. You cannot have a mathematical equation or function that goes like this. So how do you actually check this? Well, it turns out that checking of this balancing symbol is fairly easy on the stack. And what you need to do is this: you make a stack, you make an empty stack. Then what you do is for every opening symbol that you see, you would actually push that onto the stack. And when you see a closing symbol, for example, right parenthesis or right bracket, then what you will do is there are three conditions. If the stack is empty, now obviously this is an error. Otherwise, you will pop the stack. And when you pop the stack, you want to make sure what you popped out really matches with your closing symbol. If they don't match, this is another error that you are facing. Lastly, you could also, again, check if your stack, at the end of all the program is done, you still have something on your stack. That means that there's still something wrong. There's unclosed symbols. So there are really three cases. Again, first is if the stack is empty, that's an error when you want to pop something out. And if you pop something out, you want to make sure that the symbol actually match. Lastly, when you finish checking all the program, you want to make sure there's nothing on the stack. Because if there is, that means that there are still some unresolved symbols. Then that is also an error. So what can we do with this? One of the applications is to implement a reverse Polish calculator. Now, let me talk a little bit about what a reverse Polish calculator. The calculator that you use these days are really what we call an algebraic form. They're in the algebraic form. So you would write it out. 1 plus 3 is equal to 4. Straightforward. So you would actually, on your calculator, you would type 1 plus 3 equal, and it gives you the answer 4. That's what we call a kind of infixed form, because the symbol of plus, for example, is in between the two operands. The operator plus is between the two operands. 1 plus 4. 1 and 4 are operand, and the plus is the operator. And this is what we call an infixed form. However, I'd like to introduce to you what we call a postfix form, which is what we call the reverse Polish form, or what we call a suffix form. When the operators, this is the case when the operators are written after their operands. So in a typical 1 plus 4, the way that you would write it is 1, 4, and plus. Okay, 1, 4, and plus. So the infix, for example, for A times B, infix is actually 8 times B. For the prefix, you will put the time multiplication before A and B. In the postfix form, you will put the multiplication B after or behind the two operands, A and B. So again, A plus B times C will become plus A times BC in the prefix form, and ABC times plus in the postfix form. Note that the prefix and the postfix form are not related by taking minor mirror images or other such simple transformation. Okay, so there's not a simple transformation. Now, the major advantage of both Polish form is that no parentheses are needed to prevent ambiguities in the expression. So if you were to actually look at this expression, x equal to minus b plus b squared minus 4 times a times c raised to the 0.5 power divided by 2 times a, how will you actually do this? Well, here is another example. So if I were to ask you to evaluate a plus b times c plus d divided by e, you can see that there's so many parentheses around. But the way that I would write it in the reverse Polish notation would be ab plus, that will give you a value, c times d plus and e divide. Similarly, for a plus b times c plus d divided by e in the second example, I would have written it as abc times plus de divide and plus. Now, you might say that, this is actually very cryptic. However, if you look at this, it turns out that the stack will be a perfect way to actually evaluate this. For example, right here, what you see is this. To evaluate the first example, you would push A, push B. When you see the plus, what you would do is you pop the top two values and you perform that operator and push the value back again. So in essence, AB plus, you would actually have A plus B. And on the stack, you would have that value A plus B. Then when you push C and you do the multiplication, you would actually take the A plus B value and the C value and multiply them together again. This then will be pushed back to the stack. Then when you see a operand D, you will push that onto the stack. When you see operator plus, then you will actually pop the two top values out and perform the operator. And then push the value, the final result, back to the stack. So when you do this, for example, at the end of the evaluation of a mathematical equation, then you would actually have the final value on the top of the stack. And this is how a stack can help to evaluate what we call a reverse Polish notation. There are other things that you could do. For example, there are two examples here. You're a railroad operator, and you are to ask the C whether you could rearrange the cart in any order by using an auxiliary track. That's very similar to a stack. You're also asked by the boss which sequence of permutation will give rise to the most number of operations performed. So these are the type of the question that you would ask. And a stack as a data structure can help you to write an algorithm to obtain the solution for these type of problems.